Welcome to section 1.6, part A. Let's start by clarifying something that you've been using for a good while, the radian measure. The book says the radian measure of an angle ACB at the center of the unit circle equals the length of the arc that ACB cuts from the unit circle. What does that really look like? Well, first you have to be able to think about arc length. So arc length is the distance along the edge of a circle. And we think of it as being part way around, like it's not the whole circumference, but the arc length is part of the way around a circle. When we measure using the units radians, what we're really doing is we're measuring in terms of the distance around the circle. So for example, if I wanted to talk about a particular angle, we often call angles theta. This is the Greek letter theta. Let's suppose I wanted to talk about the angle that has a measure of 1 radian. What that actually means is that theta is an angle that's just wide enough to create an arc along the edge of the circle that's exactly the same length as 1 radius. The radius of the unit circle equals 1. So 1 radian means that this arc length is exactly as long as this radius. And there's one particular angle that would allow that to be 2. Similarly, like 2 radians would be an angle big enough so that the arc length on the edge is 2 times the distance of the radius. So example 1, we're just going to use the real meaning of a radian to find arc length. It says find the length of an arc subtended. Subtended just means carved out, basically, on a circle of radius 3 by a central angle of measure 2 pi over 3 radians. So we want to find an arc length. If you visualize it, we want to find the distance along the edge. And we're told that the radius of the circle is 3. And there's a very simple formula to do this. Arc length is always going to equal the radius times the angle, as long as we're talking about the angle measurement in radians. And that's exactly what it means. So for this one, the arc length, we'll call it A, is just going to be 3 times 2 pi over 3. The 3's cancel, and we get 2 pi. And that's the distance around the edge of the circle that corresponds to that angle measure. The book has another figure of this if you want to look at their solution. It's pretty simple though. So the reason that we're talking about radians is because we're interested in trig functions. When an angle of measure theta is placed in standard position at the center of a circle with radius r, and look at the figure down at the bottom of the page if you need to, then the 6 basic trig functions of theta are defined as follows, where r is the radius, and think about the fact that x and y are the coordinates of a point. We can use these definitions to help us think about what the graph of a trig function really is. When we graph trig functions in the coordinate plane, we usually denote the independent variable in radians by x instead of theta, but the input really is an angle measurement. It's a good exercise to compare the graphs on the next page with what you get in a grapher, but before we look at those shapes, I would like to make sure that you understand really where they come from. Let's take the sine function as an example. If we want to talk about this as a function, the function f of x equals sine of x, the input of this function is going to be the angle measurement. So x on this graph, this direction, is really a measurement of an angle on the unit circle. And the output of this function is going to be the value of sine. Now, way back when you first learned about sine in geometry, you probably remember SOHCAHTOA. In other words, sine of x is opposite over hypotenuse. That was just kind of the definition. So the input is an angle measurement, and the output is this weird ratio. We can get that weird ratio from the unit circle. You may have memorized what it is, but I want you to see where it comes from. When we mark this angle out, not only does it create an arc length, it also creates a right triangle. And that's the right triangle that we see right here. In fact, this point on the unit circle has coordinates x and y. And these coordinates correspond exactly to the length of this side down here, and that's x, and the height of this side over here, and that's y, because that's what it means to have a y coordinate. It's how high up is that point. Now don't get confused. The x and y over here are separate from this graph. This is the unit circle. This graph, we're trying to figure out what inputs go with what outputs. Now, the output of theta, if we plug in some angle theta, is going to be y divided by the hypotenuse. But the hypotenuse on the unit circle is 1. So really, the output of the sine function is just the y value of the point that you get when you go theta degrees along the unit circle. Now you're used to that. You're used to just taking the y value. This is why it works, though. It's opposite over hypotenuse, just like you're used to. And that's just for sine. Obviously, for cosine, it would be adjacent over hypotenuse, which is why cosine is corresponding to x on the unit circle. Using that understanding of what the input and the output is, we could make a little function table if we wanted to. Oops, sorry. Okay, the function table would be x values for this, which are theta values, and y values from the unit circle, which are sine values. And you know what they are. You know that if we plug in 0 degrees, the y value of this point right here is also 0, which is why 0, 0 is the first point on the sine graph. And you know that if we plug in pi over 2 for theta, well, pi over 2 is the angle that's all the way up here, and the y value of this point is 1, so it comes up to here. And then if we go all the way around to pi, we end up back with a y value of 0, and that's where this shape that's familiar should come from. And of course, it continues to repeat as we go on and on and on. Using that perspective, it should be easier for you to memorize these shapes. Now there's a couple key features to trig functions that you're going to need to know. Here are the standard 6 trig functions. You need to be able to find or to know off the top of your head the domain and range for each of these. Domain is pretty easy for sine and cosine because it goes through the whole x-axis, but the range is limited, and that's really important. This function never goes above 1 or below -1. For the tangent and cotangent functions, the range is everything, but the domain is restricted because there are asymptotes every so often, and there are an infinite number of asymptotes, so you should recognize when there is an asymptote. We're going to talk next about something called periodicity. You will need to know what the period is, but let me explain it before you come back to memorizing it. On a final note, you should also make sure that you know where the intercepts are for these functions. Obviously, they will change when we're no longer looking at the perfect cosine or perfect sine function, but make sure that you know what these points are. Periodicity. When an angle of measure theta and an angle of measure theta plus 2 pi are in standard position, their terminal rays coincide. If you think about our unit circle picture that we looked at a second ago, if I made this theta big enough to go all the way around the circle, it would end up back where it was at 0. So that point, the point with the x and the y value are the same. So what that means is that the two angles have the same trigonometric function values. Cosine of any angle plus 2 pi is the same thing as cosine of the original angle. Same is true for all of the trigonometric functions. Similarly, you could also subtract it because going the other way around the circle would also land you at the same point. So cosine of theta minus 2 pi is the same thing as cosine of theta, etc., etc. We see this visually when a function repeats at regular intervals. The formal definition of a periodic function, all of the trig functions are periodic, is that f of x is periodic if there is a positive number p such that f of x plus p equals f of x. For the trig functions, this p value is 2 pi. I'm going to pause while the kids walk by. The smallest such value of p is called the period. So visually, here's what this looks like. We have some sort of function, and on its graph, obviously it has some points, so let's consider these 3 points, 1, 2, 3. And obviously there are more points connecting it, but after a certain amount of time, those 3 points are going to repeat. So maybe they repeat right here, 1, 2, 3. The period is the distance between the first point and the point of its repetition. So this distance right here. Now, if these functions are curved and connected, this function, for example, might look something like this. The whole shape would have to repeat again. It's not just that one point repeats, but the whole shape is a repeating segment. And the period is the length of that little piece that then repeats over and over and over again. And the thing that's repeating is the heights are all the same, even though the x values are different. As we can see, the functions cosine and sine and secant and cosecant are periodic. Tan and cotangent are also periodic. They have a different period, which is pi. Even in odd trigonometric functions. The graphs above suggest that cosine and secant are even functions. Think about the symmetry. The other 4 basic trigonometric functions are odd, and we can prove this algebraically. So, next example, let's remember how to show that something is even or odd. So the formal definition of even is that if I plug in a negative x to the function and simplify, I'll get the same function back. Odd is when if you plug in a negative x and simplify, you get the negative version of the same function. With that reminder, let's try it for cosine and sine. So our first function is f of x equals cosine of x. Well, if I plug in a negative x, f of negative x is going to be cosine of negative x. At first glance, that doesn't seem very helpful because I don't know what to do. There's no way to simplify that. But if you go to the graph and you think about the actual x and y values, cosine looks like this, and then it goes on to both sides. If this is my x value, and I plug in the opposite instead, what do I get back? Well, the y value is exactly the same. So cosine of negative x is actually the same thing as cosine of x. Another way to think about that would be through the unit circle. If we have an angle on the unit circle, this would be your x, because an angle is what you plug in. And instead of going a positive amount, we go a negative amount, that same angle. The x coordinate of these 2 points are the same, going up or going down. If you're convinced by that, we should very easily conclude that cosine is an even function. When we think about sine, it works out differently. If I plug in a negative x to sine, and we think about the graph of sine which goes through the axis right here, plugging in a positive 1 gives you a positive 1 y value. It's going to curve. And plugging in negative 1 gives you a negative 1 value. They're opposites. If you think about the unit circle, going a certain angle in the positive direction gives you a positive y value. And if we go the opposite direction, if we make the input negative, the y value down here is going to be different. In fact, it's going to be the exact opposite of the y value at the top. So this is the same thing as negative sine of x, making the sine function odd. Here's what the book has to say.